Hi everyone, in today's lesson we're going to talk about how to find limits of piecewise functions and using direct substitution. But before we can get into the algebraic manipulation of this, I'd like to go over an example graphically. Now, since we did this the other day, I actually like you to pause the video and try to do these following limits here and then hit resume when you're ready for the answer. All right, this is what I got. Okay, so if we now go to an example algebraically, what you're going to notice is that this piecewise function is actually this piecewise function. Why? We have the line 2x plus 1 when x is less than or equal to -1. So this line, if you were to continue on the pattern, it would go through the y-axis at 1, and you could tell that it has a slope of 2. So therefore, this line, if it were the whole thing, would be 2x plus 1. This is your x squared graph, and I want that from -1 to 2, -1 to 2. And this is the line y equals 4 when x is greater than 2. So here x is greater than 4. So I would like you now to pretend like the graph isn't there. And had I given you this piecewise function from the beginning, how would we evaluate it using the limits? Well, it depends on where you are. So this one is asking the limit as x approaches 2 of f of x. So we know that in order to do a limit as x approaches a whole, we need to find the limit as x approaches 2 from the left of f of x, and we need to find the limit as x approaches 2 from the right of f of x and compare those two values. If they're the same, that's what the limit is. If they're different, then the limit does not exist. So we have to look at the conjoining points, right? So we're using this line up until -1, and then we use the quadratic, the x squared, from -1 to 2. And where these two connect is at x equals 2. So you need to check the left and the right. So in this scenario, values that are greater than 2, so right, say you're on a number line here. Here's 2. Numbers that are bigger, like 3 and 4, they come from the right side. So where x is greater than 2 is the right, which is here. So we know this limit is going to be 4. There's nothing more than just 4. It's a constant. The limit as x approaches 2 from the left would mean values that are smaller than 2. So -2, +1, 0, and so on and so on. So that would be this branch. So we're going to plug in, this is called direct substitution, we're going to plug into x squared. So we're going to plug in +2 into x squared, and that gives me 4 as well. So the limit from the left and the limit from the right are equal. Therefore, the limit as a whole is 4. And what to prove to you what we just did, we plugged into our quadratic, got 4. We plugged into the line, got 4. Limit from the left, limit from the right gave me 4 when x was equal to 2. So let's take a look at the second one. The limit as x approaches -1. Again, as a whole, there's no left and there's no right. So we have to check the left and the right. So at -1, we can see that these two are the functions that I need to be looking at. Here is when x is less than -1. So again, if you have a number line, here's -1, -2, -3. So numbers that are smaller come from the left. Numbers that are bigger come from the right. So numbers that are smaller would be here, less than -1. So that's my left side. And this guy will be my right side. These are values that are bigger than -1. So we want to do the limit as x approaches -1 from the left and the limit as x approaches -1 from the right of f of x. So the left side, like I said before, we need to use this function. So we're going to plug into 2x plus 1. So we're going to directly substitute this -1 into the x. And we get -2 plus 1 is -1. And then from the right side, we're in this one, so we're going to plug into x squared. So -1 squared is 1. So as you can see, the limit from the left, -1, is not equal to the limit from the right. Therefore, this limit does not exist. And again, we can prove that by looking at our picture. What we did was we saw that at -1, we're joining the line with the parabola. So one side, the left side, is -1. The right side is 1. The limit from the left and the right do not exist because they are not equal. And that's it. So what I would love for you guys to do right now is try these two for homework, and we will start class tomorrow by going over those. Let's jump to the next page now. Okay, so let's talk about direct substitution at holes. So this limit flow chart is kind of what I want to use, and we're going to build upon it as we do more limits. The first thing you always want to do when doing a limit algebraically is use direct substitution. If you get any real number, life is beautiful, you are done, and that is your answer. If by chance you get 0/0, that means that there's a hole in the graph, and we have to do some algebraic manipulation so that we can find the limit. We will factor to simplify the expression, and then we'll substitute that value back into the simplified expression, and then we're done. So keep those steps up there for yourself, and we're going to go through a couple of examples together. So notice this example that I give you. There is a picture. I'm not going to give you the picture. I'm always going to just give you the algebraic, but I want to use this as a reference a little bit later on. So let's use our steps. We want to always, always, always do direct substitution first. So we can go ahead and write step 1 is direct substitution. Now there's a typo here. This should say +2, not like from the right, just meaning a +2. So I want to find the limit as x approaches 2 of this function. So we're going to directly substitute this 2 into everywhere we see an x. So 2 to the third minus 8 over 2 minus 2. And we know the top, 2 to the third is 8. 8 minus 8 is 0. Bottom, 2 minus 2 is 0. So therefore, since we have 0/0, this means that there is a hole in our graph. And we can't take the limit in this form. This is actually called an indeterminate form. We can write that down. And we'll talk more about those different types of indeterminate forms, but for now, 0/0 means there's a hole in our graph. So the way around this is step 2. We can factor this expression and simplify. So I know the top is sum and difference of cubes. So if I factor this, we have small parenthesis and then super long parenthesis. It goes a squared, ab, and b squared. So what thing to the third gives me x to the third? We should be saying x, that's our a. Then what thing to the third power gives me 8? We should be saying 2, so that's our b. And then we just are going to take a, which is x, and square it, so we've got x squared. ab means we're going to take a and b and multiply them together, so 2 times x is 2x. And last but not least is my b, so we're going to take b, which is 2, and we're going to square it. And 2 squared is 4. And our signs, same opposite, always positive. So since my original sign is minus, that's same, opposite of that, always positive. So my factors are x minus 2 times x squared plus 2x plus 4. And my denominator is my x minus 2. What you should notice that these x minus 2's cancel, and you're just left with an expression of x squared plus 2x plus 4. So now we can go and jump to step 3. Step 3 is we are going to try direct substitution again. With this new simplified version up here. So we're going to plug in our x equals 2 now into that simplified equation. So we're going to try 2 squared plus 2 times 2 plus 4. So quick mental math, that gives me 12. Now 12 is going to be your answer to your problem. So the limit, this whole thing up here, is 12. And let's prove it to ourselves. This is the graph of this function here, of this rational function. Here's my graph. So what happens? The limit as x approaches 2 from the left is 12. The limit as x approaches 2 from the right is also 12. Therefore, the limit is 12. All right, what I'd love for you guys to do right now is try an example number 2. Try this one for homework. See if you can verify it with the graph, and then we'll go over it tomorrow in class. All right, have a good night.